Okay, we're off to chapter 12, bonding, as we finished up chapter 11 last time, electron configuration, periodic trends. So in this chapter, we're going to talk about the two types of bonding. We're going to talk about ionic bonding, which, as we will see, is obviously between a metal and a non-metal. And as a result of those periodic trends that we talked about in the last chapter, when these two guys get together, there is a great difference in terms of their periodic trends, in terms of who wants to keep their electron, who wants to get rid of their electrons. And there's such a good difference between them that what we always get is this transfer of electrons from the metal to the non-metal, because remember, the metals pretty much have all those trends that want to give away their electrons. Non-metals have all the trends where they want to gain their electrons. The result of that is we do create ions, things with charges, and in an ionic bond, it is that transfer of electrons, or the opposites attraction or electrostatic attraction, that holds that together. There's no sharing of electrons involved. Now, we will also talk a lot about covalent bonding. And covalent bonding, as we will see, is a little bit different. It's between two nonmetals. And because it's really between two nonmetals, and as we talked about last time as well, they're pretty much in the same location on the periodic table, which means they both want to hang on to their electrons. So neither one of them really wants to give away their electrons. So the best that they're going to do is going to have some type of sharing going to happen with those electrons. And as we will see in this chapter, the sharing may be equal sharing, it may be unequal sharing, but there is some aspect of sharing between those two atoms that basically is what holds that bond together. So let's get into this a little bit here. Lewis dot symbols were sometimes just more generically referred to as electron dot symbols. These are basically symbols that are used to represent bonding, both ionic bonding and covalent bonding that's occurring. And when atoms come together, it is the electrons that basically see each other. Thank you. And come in contact with each other. And it's really those outer electrons, which are those valence electrons. So when we talk about bonding, it is those valence electrons that are involved. Remember that the quick way that you can figure out the valence electrons is it is equal to the group number. So the number of valence electrons that an element has will equal the group number it is on the periodic table. You can also get it, obviously, from writing the electron configuration. It is the highest energy level electrons, but again, that's a much, much quicker way to do it. So a Lewis dot symbol, like I said before, is pretty much just the symbol, whatever it may be. We use one dot to represent each of the valence electrons that the atom has. There is really kind of no necessary rule in a sense, other than typically we do not put more than two dots per side. So two dots per side. A lot of times people go one dot all the way around and then kind of pair them up, but it doesn't really truly matter. But other than that, kind of no more than two. Two per side, there's four sides. That is 8 electrons. And 8 electrons is the same as the noble gases on the periodic table. And as we probably talked about when we did electron configuration, that is really the purpose, for example, of all bonding, both ionic bonding and covalent bonding. The purpose of it is for everybody to achieve noble gas configuration, or the same electron configuration as the noble gases. And that's really the goal of it. That is for everybody, as we'll talk about, except for hydrogen, because again, if you look at the periodic table where hydrogen is located, the noble gas that comes after hydrogen is helium, and that is only 2 electrons. So hydrogen should never, ever have more than 2 electrons. Pretty much, as we'll talk about, everybody else wants pretty much 8 electrons to be stable and like the noble gases. So here is obviously some Lewis dot symbols. And as you can see, everybody in group 1 has 1, 2, 3, 4, 5, 6, 7, 8. One exception, obviously, for group 8 is helium. As I just mentioned, it only has 2 electrons total and both of them would be its valence electrons. So obviously, even though it's a member of group 8, it only has 2 total electrons, so it can't have 8 electrons to be stable. Good news in bonding, we really don't deal too much at all with the transition metals in terms of bonding. So that what that means is we don't have to worry too much about their valence electrons, but we also talked about that it is the group number. Remember, if you're rolling with the transition metals, it is kind of the 1 through 18 numbering that you would use for the valence electrons for our transition metals, as they have the s electrons and they also have the d electrons available to them to kind of use as valence electrons. So that's sort of the numbering if we go through the middle section there. But like I said, good news is you probably won't see any of that in terms of bonding. So elements that form ionic compounds, first off, we're going to use our Lewis dot symbols to help us identify those 2 types of bonding that we talked about. Again, either our ionic bonding, which once again, you absolutely know it's ionic when you have this combination of our metal and non-metal, or if it's covalent, you got some non-metals together, that is definitely the situation. General rule is things with low ionization energy will tend to form cations. So things with low ionization energy, which is the energy required to remove an electron, if it's low, it means you could remove an electron relatively easy. And those guys typically will become positively charged and cations. Guys with high electron affinity, those are the energy change that occurs when somebody gains an electron. So same idea, if somebody has high electron affinity, that means that they're probably gaining electrons, and they most likely will make anions. So kind of what we've been talking about, the general rule tells us everybody to the left there, metals pretty much are going to be positively charged. Upper right of the periodic table, they're going to kind of roll into the negatively charged anions. And again, a lot of that is based off of those periodic trends that we talked about in the previous chapter. So let's take a look at lithium fluoride, which is an example of an ionic compound. And I know this is ionic because hopefully you could identify lithium as a metal. Fluoride, which is really fluorine, is a nonmetal. And once again, whenever you have that combination, it's pretty much ionic. You don't even really have to think about it or second guess it. It is definitely going to be ionic. So if we were to represent ionic bonding here, which again is basically a transfer of electrons happening here, we will start with lithium, which is group 1 and has 1 valence electron. We throw back a little electron configuration on it, a 1s2, 2s1, this right here being that 1 valence electron that we see in the picture. This obviously being its core electrons, right, as we've talked about before. We take fluorine, which is group 7. That means it has 7 valence electrons. Also, if we lay up a little electron configuration, 1s2, 2s2, 2p5, and right here is the 7 valence electrons there for fluorine. Once again, when we put these 2 guys together, because we have sort of extreme, if you will, we have a metal and a non-metal. That metal is going to go take my electron, so it's going to give up its electron over to the fluorine. The fluorine is going to go thanks because in a p subshell we could hold 6 and it only has 5 right now, so it's got a place to put that electron basically. And when it does so, it's at that point that lithium will now become positively 1 charged because it lost 1 electron. The fluorine there will pick up the electron. And because it picked up an electron, it will also pick up a negative charge. And this would represent basically an ionic bond that is formed. When we draw this for Lewis symbols, we do want to include the charges here because it is ionic and these are ions. So when you draw it for something that's ionic, you should include the charges. I would say typically speaking, at least one of them goes into a bracket. Sometimes people will bracket everybody in an ionic situation to also indicate that they're not sharing those electrons. So we have ions here that are keeping them attractive. So I would say at minimum, you should at least bracket one of them. And again, sometimes people will bracket both of them. What happens though in terms of its electron configuration is this lithium that loses its 1 electron, its valence electron, will now have an electron configuration of 1s2 that is the same as being neon's configuration. Fluorine, by putting that electron right about there, will now have an electron configuration in the fluoride version, 1s2, 2s2, 2p6. That is 10 electrons are neon's configuration. I over neoned it. The first one's helium with 2, actually, not neon. So the first one there is helium with 2 electrons, and neon here with our 10 electrons in this particular case. Now, what we can see here is this is really, once again, the purpose of ionic bonding is for everybody to achieve noble gas configuration. So they have now achieved the same electron configuration as noble gases. Remember that the noble gases are really stable. They're chemically inert. They're not looking to react or anything like that because they're pretty much happy the way they are. And that's really the goal of everybody else, is to try to be just like them. Once again, as we've talked about probably a number of times, they do not become these elements, and that is because their protons don't change. So the only thing that happens is they now become very much like them, isoelectronic. They have the same electron configuration as the noble gases. Questions on that there? All right, let's take a look here at another one. Let's take a look. Actually, as I mentioned before, that is an ionic bond. Once again, it is that attraction here between the positively charged cation and the negatively charged anion that holds that together. Once again, there is no sharing of electrons happening here in an ionic bond. Take a look at calcium oxide. Calcium is group 2, so that means that it does have 2 valence electrons. It also has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. Or if you want to shorthand it, that's a little argon 4s2 action happening. We have our oxygen, which is group 6. And here in this situation, 1s2, 2s2, and 2p4. This is the 6 valence electrons for oxygen. This obviously is the 2 valence electrons there for calcium. So with our metal and non-metal coming together here, calcium is going to want to lose an electron here. And calcium is going to want to lose 2 electrons here over to the oxygen. That is good because the oxygen in this case actually has room for both of those electrons right there in its p subshell. So it's got some room to accept them. The result of that is calcium will now become a +2 charge as it's able to lose both of its electrons. The oxygen will gain those 2 electrons. And once again, because it gains the 2 electrons, it will now become a -2 charge. Once again, what's holding that together is the positive negative attraction between those ions. Once again, no sharing of electron. As we look at what's happening here with calcium, it's going to be these 2 valence electrons that gets lost, which means calcium here has a configuration of 1s2, 2s2, 2p6, 3s2, 3p6. That is argon's configuration. Once again, our oxygen picking up those 2 electrons right there will now become the oxide ion and have a couple of extra electrons, and that is moving it upwards to 10, which is neon configuration. Once again, in this case, the whole purpose of bonding is for them to reach noble gas configuration, and they're able to do that. And that is typically what happens with our ionic compounds and our metals and nonmetals. The idea here is the metals will lose electrons. If you look on the periodic table, they will back up to the noble gas that comes right before them on the periodic table in terms of their electron configuration. The nonmetals will actually gain the electrons and actually move forward on the periodic table and have this same electron configuration as the nonmetals that come before them. Any questions on that there? Now, what happens if we maybe slap both of these together? Bless you. So Let's say we started with calcium here with its 2 electrons, and again, its configuration of argon 4s2. We pop it together there with our fluorine that we saw earlier, which had our 1s2, 2s2, 2p5. In this case, what's going to happen is the same sort of idea. We're going to get our calcium that's going to send over to fluorine one of those electrons, which it can handle right there. At this point, though, we run into a little problem, and that problem is, can this fluorine take any more electrons? It cannot. And is calcium going to be happy losing just 1 electron? It is not, because if you look at the periodic table, if it loses just 1 electron, it only moves back to potassium, which is not a noble gas. So it needs to lose 2 electrons again to reach that noble gas configuration. So in this particular case, because that fluorine can only hold 1, we do not just need one of those fluorines, but we actually need a second fluorine that is capable of accepting the other electron in this particular case. The result of this is calcium was able to get rid of both of its electrons, one to each of the fluorines, so it becomes now a +2 charge. Each of the fluorines here will actually only pick up 1 electron, which means it has a -1 charge. And there's a second fluorine here that also only picked up 1 electron and has a -1 charge. The result of that is calcium here, by losing both of its electrons, will now achieve argon's configuration. Both of these fluorines, which put them right there into that p subshell, each putting an electron in there, will get those guys up to 10. And each of these fluorines achieve noble gas configuration by getting to the same electron configuration as neon. In this case, all 3 of these ions are able to achieve noble gas configuration by, again, transferring, accepting, and donating electrons over. Question on that. This is really the main reason, if you remember, perhaps when we talked a little bit about writing formulas for ionic compounds, and when we take 2 ions together, like a calcium ion and a fluoride ion, and we put them together, we want to make sure that the overall charge equals 0. And that is why I said earlier you actually need 2 of these guys to do that. And the real reason is not really balancing out to 0, but when you do balance it out to 0 in the simplest way possible, what that does in terms of the bonding that's happening is it allows everybody there to achieve noble gas configuration. If you did not balance out the charge and just left it like this, for example, with a plus charge, that would mean that the calcium here actually only got to +1 and would not be able to have lost enough electrons to be stable. And again, that's why when we write formulas for ionic compounds, we always want to make sure it equals 0. And the real reason is the bonding reason allows everybody to reach noble gas configuration and be really stable. Yes, sir. There is 2 fluorine. Are we talking about the formula up here? Here, yeah. We're talking about which, the very bottom, like down here. Yeah. It does. I didn't really balance it. So if we were balancing it, really, technically speaking, there would be a big 2 in front of there, and there would be 2, just like up here. There's actually 2 of these guys, basically. Yeah, yeah, I guess, yeah. So if we wrote it as like a balance equation, you would have a 2 in front of it. Yeah, yep. Other questions? All right. Which I guess I got here by drawing it right here. Actually, there are 2. All right. Any questions on ionic bonding? There. So ionic bonding, we could use Lewis structures to help us show it. We do need to include the charges when we do that. And now let's talk about covalent bonding. As I mentioned before, covalent bonding is different. This is usually between 2 nonmetals. And in this particular case, what's going to happen, Gilbert Lewis suggested the idea of covalent bonding as things sharing electrons, hence Lewis structures. So if we look at like the hydrogen, for example, hydrogen has one electron, one electron. So because they are both hydrogen, for example, in this case, which they are both nonmetals, neither one of them is going to want to give away their electrons. They basically have the exact same periodic trends in this case. So, like I said, neither one's going to give up its electrons. So the best that they will agree upon is they will share these electrons. So what happens is they decide to actually share these electrons between them. And the result of that is you make a covalent bond where those electrons get shared. And those two electrons between the hydrogens will count for the hydrogen on the left, which gives it 2 electrons. It will also count for the hydrogen on the right, which gives it 2 electrons. And as we talked about earlier, right, hydrogen just needs to get to helium number 2 there. And that's going to make it really happy and stable in this particular case. You could also represent this sharing of electrons with a line. One line represents a pair of electrons or 2 dots there, and that obviously is referred to as a single bond. You could have a double bond, as we'll talk about, which is 4 electrons or 2 pairs. And as we will see, you could also have a triple bond, which is 6 total electrons or 3 pairs of electrons for a triple bond. So you can think of this as what kind of holds those guys together is there's kind of like the nucleus, if you will, in these guys. And the electrons, which are negatively charged, are going to be attracted to the nucleus, say to the hydrogen on the left, but they're also going to be attracted to the nucleus of the hydrogen on the right. So that kind of dual attraction to both nucleuses there will essentially lock those electrons in place between the 2 atoms. And that again is a covalent bond. Different than ionic here, we have sharing of electrons that are occurring. And again, that kind of dual attraction to the nucleus sort of locks everybody into place. Now, if we look at another example like fluorine, and as we saw with his electron configuration, we would have, in terms of fluorine here, 7 valence electrons, as it is group 7 on the periodic table. Once again, because they're really 2 nonmetals, and also in this particular case, also identical to each other, they are going to end up sharing those electrons rather than transferring. So we will get a pair of electrons between the 2, which are going to be shared. And once again, in this case, by sharing those electrons, those 2 will count for the guy on the right, and those 2 will count for the F on the left. That's going to give each of these fluorines 8 electrons, which has a key, as you can see, pretty big number here. That is our noble gas number. That's going to allow each of them, once again, to become very stable in terms of their electrons, just like the noble gases here, and reach that sort of noble gas configuration. Just like before, you can represent those electrons that are in the bond with a line rather than dots. I personally use lines most of the time for electrons in a bond, or bonding electrons. But if you want to use dots, it's not wrong to use dots between them as well. Any questions on that there? Now, when we do look at this sort of picture here, all these dots here, which are not involved in bonding, and we know they're not involved in bonding because there's no other element basically written on the other side of it. These have a special name. These are what are known as lone pairs, although books these days call them non-bonding electrons. So if I say lone pairs, which is kind of what I use a lot, that's the same thing as non-bonding electrons. So I would say nowadays books actually use more non-bonding than lone pairs. Now, if we look at the electrons that are actually being shared within the bond, these guys right here, they also have a very creative name since they are involved in a bond. These are what are referred to as bonding electrons. So we have bonding electrons, which are obviously the electrons that are making a bond between two atoms. The bonding electrons can be shown as a line, or it can be shown as a pair of dots. The non-bonding electron or lone pairs are not involved in any type of bond formation, and they're usually only shown as the pairs of dots. So you should only show them as pairs of dots. When you draw Lewis structures, which we'll talk about how to draw these properly, you should always include all the bonding electrons and obviously all the non-bonding electrons as well. So you want to make sure in your picture that you include all of those electrons. So a Lewis structure, as we've seen, basically for covalent bonding, shows again those bonding electrons as a line or a pair of dots, and our lone pairs as just dots. Remember again here, although in these pictures we're showing electrons, we are only showing really the valence electrons because they are the only electrons involved in bonding. Remember that each of these elements have core electrons, which are lower energy electrons that are not shown in these pictures or not involved in bonding, which is why they're not shown there. But they still have, obviously, their lower energy electrons or core electrons as well. So let's take a look at water. If you draw up a Lewis structure here for water, once again, you can see that in this particular case, the oxygen is sharing electrons here with both of the hydrogens, and that's going to allow, once again, oxygen to move forward to 8 valence electrons. Each of the hydrogens here have its 2, which is, again, all that hydrogen should ever have. I cannot say that enough. Hydrogen should only look like this pretty much ever. You should never have hydrogen with dots because that's a super sad face. Hydrogen with dots and a double or triple behind it's a double super sad face and an X. Yes, so never draw any of those things. Hydrogen should pretty much only look like what it is on the left. It also should always be on the outside of the molecule because if you put hydrogen in the inside or the center, it will have more than 2 electrons for sure. So it never should be in the center, always should be on the outside. Pretty much should only look like that, or if you use dots instead of lines, should pretty much only look like that. Yeah. Any questions on that there? That brings us to the 2 important rules there. The octet rule, which is that 8 rule. It basically says that, like we've been talking about, the purpose of bonding is to reach noble gas configuration. So everybody will really continue to make bonds until they have 8 valence electrons around them. And that is obviously, except for what we just talked about there with all the unhappy faces, which is hydrogen, which is sometimes referred to as the duet rule. It will only have 2 electrons and should never have more than 2 electrons because really all it needs to get to is helium on the periodic table there to be stable. Now, that is really the goal for this class, is to meet the octet rule. And sometimes to meet the octet rule, all you need is basically single bonds to do it. Sometimes you may need double bonds to get to the octet rule, and sometimes you may actually need triple bonds to get something to the octet rule. But as we'll talk about, usually you want to start out in the single bond approach and kind of work your way to double bond and triple bonds. And a mistake that a lot of people make is they try to kind of double bond, triple bond right out of the box when they're drawing these Lewis structures, and you really should sort of save that kind of for the end if you need to use it only. And again, usually the octet rule a lot of times can be met by just making single bonds along the way. So again, talking about that, a single bond, as we talked about a little bit earlier, is where 2 atoms are basically sharing 1 pair of electrons. That is 2 dots again, are 1 line. So we can meet the octet rule here by just single bonding it up. A pair of electrons are 2 dots. And again, by that single bond, as we talked about, that allows both of these guys basically to meet the octet rule. As I mentioned earlier, just a second ago, sometimes you need to go a little further to do that. So something like carbon dioxide actually has 2 double bonds and is necessary for the carbon there to get to 8 electrons. And by doing so, that also keeps our oxygens also at 8 electrons each. And in this particular case, it actually requires 2 double bonds to allow everybody to achieve noble gas configuration. Once again, our double bond being obviously 2 lines, which represents 2 pairs of electrons or 4 total electrons in this particular case. And as I also mentioned, sometimes it does require a triple bond to get there. And that is, for example, something like nitrogen. By taking a triple bond, which is basically 3 lines, are sharing 6 electrons or 3 pairs of electrons. That allows everybody to achieve noble gas configuration. So each of those nitrogens there, by sharing that triple bond, 2 dots for each line, gives us 8 electrons. And on the bottom here, the carbons also get to 8 electrons. Here we still see our friend hydrogen sharing with the carbon, but only going to 2 electrons, which once again is all it should have. Any questions on that? Yeah. 1 or 2 dots on each side of. There is. Which one are we talking about? In this case, there's an exception to that. Really, I don't know if it's really an exception or not, but in this case, we do put them together because they're all part of a bond. So that indicates that all those electrons are being shared between the two. Yeah. So overall, though, if you overall, it's basically they would technically be distributed, but because they're going to be kind of moved into the center to be shared between the two, we do represent them in a sort of bonding situation. More than 2 is okay, yeah. But if you're just drawing, say, a Lewis dot symbol by itself, say just like nitrogen by itself, you typically don't go more than 2%. Other questions? All right, so let's talk a little about electronegativity, which, as we talked about previously, is the ability of an atom to bring electrons towards itself and remember, on the periodic table, it increases as you go up to the right, decreases as you go down, and it is fluorine that is the most electronegative element that we could have. So electronegativity really is the biggest sort of determiner in terms of what happens in terms of electrons when they're like between 2 atoms. And what I mean by that is we could use electronegativity to help us decide, will those electrons be shared equally? Will those electrons be shared unequally? And although you don't really need electronegativity to do this, you could also use it to determine whether or not those electrons will actually not be shared at all, but actually be transferred from one to the next. So when we look at something like hydrogen in this particular case, as we talked about, it's going to share its electrons there. And because both of these guys within this bond are hydrogen, they both have identical electronegativity, which means essentially, if my little lines here are like the electron density, the electrons are going to feel basically the same pull towards each hydrogen. And the result of that is you're going to end up with equal sharing of electrons in this case. And the result of equal sharing of electrons means that there really is no negative side or positive side to that bond. It's almost like a neutral bond. The electrons are really spread out equally over the entire bond. Everybody's sharing them equally. They're not all piling up on one side versus the other. And it creates like a neutral bond. And really what this creates is whenever you have equal sharing of electrons, this is what is known as a nonpolar covalent bond. Although most people just kind of call it a nonpolar bond, the covalent is sort of implied. So when you have a nonpolar bond that is sharing of electrons that's equally, If you have perfect equal sharing of electrons like what we have here, this is sometimes referred to as a pure covalent bond. That's like the perfect equal sharing of electrons. By the way, that is still a nonpolar bond as well. So, but sometimes books and stuff will classify a bond where it's like the perfect equal sharing of electrons since you have two of the same. They'll sometimes call that as a pure covalent bond, which is still nonpolar, still perfect equal sharing of electrons. We'll see here that there can still be a equal sharing of electrons, even though not perfect equal sharing, but it's still considered close enough to being equal sharing of electrons. So this type of bond is, like I said, a nonpolar covalent bond. But what happens if we switch out one of the hydrogens for fluorine? And in this case here, if we make our bond with fluorine, we now have basically a difference in electronegativity values for these things. As we just talked about, the most electronegative element you could have is fluorine, which means between fluorine and hydrogen, the electron should head towards which one? Hydrogen or fluorine? Electron should head towards fluorine because it is the most electronegative element, and electronegativity is the ability to bring electrons towards yourself. So because it's more electronegative, it's going to have a greater pull of those electrons towards itself. The result of that is, if this is sort of the electron density, we would see a much greater electrons heading that way than, say, over at the hydrogen side. Now, the result of this happening is the electrons are kind of shifting towards the fluorine, and that's going to create on the fluorine a partially negative charge, and it's going to create a partially positive charge on the hydrogen. That's a delta symbol. And we could also represent this sort of difference with an arrow, which is sometimes referred to as a bond dipole arrow. And this arrow points towards always the side that is more negative in the bond. And this back part that makes like a plus sign is to the more positive sign or positive side of the bond. Now, this type of bond is what is known as a polar covalent bond, or just simply a polar bond it's referred to. And this is a result, as we can see here, of unequal sharing of electrons. Why is it, in this case, only a partially positive charge and a partially negative charge rather than a full positive charge and a full negative charge? Why is it only partially positive, partially negative? Yeah, because there is still, again, some aspect of sharing that is happening here. So because they are still sharing, it is only partially positive and partially negative. It's kind of like tug of war. The fluorine's pulling on the rope pretty good, but the hydrogen is hanging on. He's just being dragged a little bit. But he's still hanging on to the rope. He hasn't fully let go of the rope. And that's different than what happens in an ionic bond, because there's such a great difference in electronegativity between metals and nonmetals. The metals don't hang on anymore. They just let the electron go. The nonmetals completely accept the electrons, and now we get that transfer of electrons, which gives our metal a positive charge and our nonmetal full negative charge. Here, because they're still sharing, it's only partially positive, partially negative. Any questions on that there? So again, this is a polar covalent bond, unequal sharing of electrons. And again, we could represent that with that arrow there, which is our dipole arrow. What we're talking about here is sort of bond polarity, and this is what is known as a polar bond. And again, it is really a polar covalent bond, but most people just call it a polar bond in this case. And this will always occur when you put basically two atoms together where those elements have a fairly good difference in electronegativity, not an extreme difference, but a relatively good amount of difference in electronegativity, you'll get this unequal sharing of electrons that are occurring, as we can see here, and then our little arrow guy there. So when we think about sort of the three types of bonding that we talked about, you could think on one end of the extreme, we have ionic bonding. And that again is always between a metal and a non-metal. And as I mentioned, because of that difference in those periodic trends, this is going to result in that transfer of electrons, creating a cation that's positively charged, anion that's negatively charged. Once again, that electrostatic attraction and no sharing of electrons. An example would be any ionic compound like sodium chloride, for example. On the other end of the extreme, you have a nonpolar covalent bond. And that is always between two nonmetals. Here we actually have equal sharing of electrons. And an example would be any of those guys that we did, H2 or F2. Our example of that. Now, kind of in the middle of the two is the polar covalent bond that we just got done talking about, or just a polar bond. Also between two nonmetals, also sharing of electrons, but here it's going to be unequal sharing of electrons. And an example of that, obviously, here is our HF. And again, the result of that unequal sharing of electrons creates a bond where there is a positive side to that bond and a negative side to that bond because of the unequal sharing of electrons. That polar bond is really important, for example, as we'll talk about in later chapters, how certain molecules are able to interact with other molecules is, if they have like a polar bond versus they don't have polar bonds, it's a big role in terms of things like solubility, boiling points, how things interact, both with themselves actually and other molecules as well. Any questions on those three types there? So let's talk a little about electronegativity to help us really determine, if I put these two atoms together, for example, how would I expect these electrons to be shared? So electronegativity really is sort of the biggest thing that you look at when you're looking at, as I mentioned before, was sometimes referred to as bond polarity. And electronegativity, as we've talked about, is that ability of an atom to bring electrons towards itself. It's based on electron affinity and ionization energy. And again, fluorine, for example, has high electron affinity and it has high ionization energy. So those are two things that basically means it's going to hang on to its electrons and want to gain electrons. So it has a high electronegativity, so it has the ability to bring those electrons towards itself. Sodium, on the other hand, has low electron affinity and has low ionization energy, which means it has two properties where it's not looking to gain electrons, nor is it really looking to hang on to its own electrons. And again, that's why something like sodium will give away its electrons and also have a low electronegativity value. So there is a way to actually sort of calculate whether or not when you put two elements together, would you expect them to make a polar bond, a non-polar bond? You can even use it for ionic, which you really don't need to. A guy by the name of Pauling came up with a scale where electronegativity runs from 0 to 4. 4 is the most electronegative. 0 being not so much here. And if you calculate the difference in electronegativity values, which is sometimes abbreviated like that, and the way you do that is simply just take the two values, one value for each element in the bond, and you subtract them. And you subtract the larger number from the smaller. That way you always get a positive number. If If you end up with anywhere from 0 to 0.4, that is usually considered a nonpolar covalent bond. If you're above 0.4, which I guess would be 0.5, to less than 2, that is usually some type of polar covalent bond, unequal sharing of electrons. First one being equal sharing of electrons. And if you're above 2, that usually is some type of ionic bond, no sharing of electrons, transfer of electrons. That is not really a perfect number, to be honest with you. There's a lot of metal and non-metals that you can subtract the numbers and be less than 2, but it's still ionic. So personally, I wouldn't even worry about ionic and difference in electronegativity values. The only thing you should worry about for ionic is I have a metal and a non-metal. Right, that it's ionic, you'll be in good shape pretty much all the time. You won't be really wrong. So I wouldn't even worry about that if it's over 2 or something like that. But you technically can use it, but 2 is just a general cutoff for ionic. It can go a little below 2, a little above 2. There could be one where it's like 1.8, but still ionic as well. So I would say most often we use difference in electronegativity to help us with covalent bonding and determining whether or not it's going to be a nonpolar bond or a polar bond, equal or unequal sharing electron. By the way, if you get a difference in electronegativity of 0, that is also a nonpolar bond, but that is our pure covalent bond that we were talking about earlier, which is also nonpolar. So let's take a look here. Here is a table of electronegativity values, and we could use this table to help us decide, what's going on. If we look at some of the examples that we saw earlier, sodium chloride, we had HF, we had F2, for example. So if we take a look at the electronegativity value here for sodium, that is 0.9. And we take a look at chlorine there, which is 3. We could calculate the difference in electronegativity here. And once again, you're just going to take the larger number minus the smaller. So you get a positive number. That's 2.1. 2.1 is above 2, which means that it should be ionic. And this should be a transfer of electrons that's going to happen here. Once again, you really don't need the values for that particular one because it's a metal, non-metal is going to be ionic. So you don't necessarily need it. We look at fluorine here. Fluorine has a value of 4. The other fluorine has a value of 4. The difference in electronegativity here going to be 4 minus 4, which is 0. That is definitely going to be a nonpolar bond, nonpolar covalent bond in this case. That is also one that could be classified as a pure covalent bond because that's like perfect equals 0 sharing of electrons. We take a look at our hydrogen here, which is 2.1, and our fluorine, which is 4, and we do the difference in electronegativity here of 4 minus 2.1, that is a 1.9. 1.9 is less than 2, but above 0.4, which means that this is, as we talked about, a polar bond, where it will always point that dipole arrow towards the more electronegative element, which is the fluorine. Question on that there. So why don't you try some, yeah. Yeah, so the polar is these cutoffs right here. So anywhere from 0 to 0.4 difference is considered a nonpolar bond. Anything above 0.4, which is basically kind of 0.5 to below 2 is polar. And then typically anything above 2 difference is ionic. But again, metal, non-metals really has to deal with that. So basically up to 0.4 nonpolar, anything above that, but less than 2, polar, basically. Other questions on that? So why don't you try some here? Why don't you do the bond between carbon and hydrogen, carbon and oxygen, sulfur and oxygen. Let's do potassium and chlorine. And let's do a little nitrogen and chlorine as well. All right. So for each of these, is it ionic, is it polar, or is it a nonpolar bond? Once again, our differences here, 0 to 0.4, nonpolar. 0.5 to less than 2, polar, and above 2, typically ionic. All right, just take a few moments there, see what you come up with. Okay, so let's take a look. We'll start with the carbon hydrogen here. So carbon is 2.5, hydrogen is 2.1. So our difference in electronegativity is 2.5 minus 2.1. That is 0.4. That means that this bond is going to be nonpolar. And that really is the reason for the cutoff being at 0.4, that particular bond there, which is the bond that you find in organic molecules like that heptane we used the other day. And those guys are nonpolar, so pretty much organic carbon, hydrogen, carbon, carbon, and that's why the cutoff goes to like 0.4. If we do carbon and oxygen there next, carbon and oxygen, once again, carbon being 2.5, or oxygen being 3.5. And the difference in electronegativity going to be 3.5 minus 2.5, going to give us a 1. So a 1 is definitely over 0.4, but less than 2. So this is going to be a polar bond. The arrow should point towards the carbon or the oxygen. Should point towards the more electronegative, which would be the oxygen, as it will be more negative, partially negative than the carbon in this particular case. Question on that one there. There is no arrow drawn for nonpolar. The arrow, again, is only for polar bonds. So we only draw that for polar bonds because nonpolar bonds are sharing electrons equally. So again, there is no side that's positive or negative. So that's why, again, we don't draw that arrow for that. We do sulfur and oxygen. Sulfur there 2.5. Our oxygen still 3.5. Difference in electronegativity here 3.5 minus 2.5, still 1 difference, which means that this guy would be polar. And once again, our arrow would point towards the oxygen side there, and that would be a polar bond. Question on those there. Looking at potassium, which is 0.8, looks like, and chlorine is 3. Difference in electronegativity 3 minus 0.8. It's like a 2.2, I believe. Different. That definitely is going to be ionic in this case. Once again, we actually don't actually need it because I hope we know that's a metal and a non-metal, which means it should be ionic to begin with. Lastly, if we look at nitrogen is 3 and chlorine is 3, which means the difference in electronegativity is 3 minus 3, which is 0. That means that this bond is actually a nonpolar bond in this case. So this brings up a really good demonstration that you definitely, if you have two of the same element in a bond, they're going to be a nonpolar because they're the same element. But it is possible to have two different elements that have the same electronegativity value, and it can create a nonpolar bond. So it is possible. The reason for that is what's sometimes referred to as the diagonal relationship on the periodic table. We also see it over here as well, and a couple other places we will sort of see that diagonal relationship. So they're diagonal of each other on the periodic table, not perfectly diagonal, kind of diagonal and over 1. And because they're diagonal and over 1, one is further up, but one is further to the right. So their differences cancel each other out in terms of their electronegativity values. So there's just that diagonal relationship that you sometimes come across that could lead to two different elements sharing electrons equally. Yes, sir. It would be nonpolar, but it'd be also sometimes referred to as a pure covalent bond. So a pure covalent bond is still a nonpolar bond, but some books and stuff will say pure covalent bond to represent the fact that it's like perfect equal sharing of electrons. Yeah, nonpolar and pure covalent bond are technically the same bond. They're both nonpolar. The classification of pure covalent is to sort of describe like that's the as perfect equal sharing of electrons as you could get, a difference of 0. Because there is sort of degrees of nonpolar bond where we still consider it equal sharing of electrons, but is it truly equal? The answer is it's really not. For example, if we look at carbon and hydrogen is considered a nonpolar bond. But there is a difference in electronegativity between carbon and hydrogen, right? A slight difference, which means, technically speaking, the electrons are heading actually in this case a little bit closer to carbon than hydrogen. but not enough that is considered a polar bond, unequal sharing. So it's still considered equal sharing, but in reality, it's not like perfectly equal sharing electrons. The electrons in that case of carbon and hydrogen are still kind of heading a little bit towards carbon, but not enough to be considered unequal. In a pure covalent bond, which is still a nonpolar bond, you have the electrons really not heading one way or the other. They're just like perfectly equally shared between them. Other questions? Yeah. Now, do you always need these values to determine whether or not something is going to be polar or nonpolar? The answer is no. You could usually make a fairly good educated guess on whether or not a bond's going to be polar or nonpolar just based on the general trends of electronegativity on the periodic table, where it increases up to the right, decreases down the left. For example, if we took our carbon-oxygen bond, well, they are actually in the same row on the periodic table, and carbon is further to the left and oxygen is further to the right. Because they're in the same row and one is further to the right than the other, you can make a pretty educated guess it's going to be a polar bond. And because oxygen is further to the right, that's most likely going to be more electronegative and create a polar bond. So if you're comparing two elements that are in the same row and they are obviously not on the same spot, that most likely, if they're nonmetals, will lead to a polar bond. You also could do the same thing with groups. If we look at our sulfur-oxygen combo here, sulfur and oxygen are in the same group on the periodic table. Oxygen is further up, which means it should be more electronegative in that group and also should lead to a polar bond. So if you're definitely comparing nonmetals that are in the same row or the same group, they most likely will be a polar bond. If you're comparing something on the left-hand side of the periodic table to something on the right-hand side of the periodic table, metal and nonmetal, you pretty much know is going to be ionic. So there's a lot you could do without the numbers and just a general idea. The only thing really you have to watch out for a lot of times is that diagonal relationship that pops up occasionally that we just talked about. But other than that, if there are two different guys in the same row, our group, most likely going to be a polar bond. Any questions on electronegativity and bond polarity? So we're going to talk about a different type of polarity as well, but this is bond polarity. What we're talking about, where you use the electronegativity difference to determine whether or not it's a polar or non-polar bond. Any questions on that there? So as we see there, atoms with really widely different electronegativity values will tend to form ionic compounds. But when we get into our sort of non-metal and non-metal region, and those guys get together, we're going to get that sharing of electron that's going to happen. And that is why, as we've been talking about, generally speaking, an ionic bond is between a metal and a non-metal. And a covalent bond will usually be those two nonmetals coming together where they will share those electrons. So this is, again, just sort of a summary of what we've been talking about. As I mentioned before, that rule of 2 and above is just a general rule for ionic. Much better just to approach it as we've been talking about. That's a metal, non-metal is going to be ionic. There's also a way that sometimes bonds are classified, and we talked a little bit about it a second ago, and that's by percent ionic character. If something is 100% ionic character, that means it's an ionic bond. If it's 0% ionic character, that's going to be a nonpolar bond. And obviously somewhere between 50% or in that area up above or below will be some type of polar bond. I would say nowadays people don't really talk too much about percent ionic character and that type of stuff. They usually just kind of talk about, is it a polar covalent bond, non-polar bond, or an ionic bond? But occasionally percent ionic character sometimes pops up, but not too much these days, I think. Any questions on the different types of bonding? So as you can see here, purely ionic, transfer of electrons, purely covalent, equal sharing, and our polar covalent, unequal sharing of electrons. Any questions? All right, I think that's probably a good place to lay it up here for today.